Thank you, Basal, for the good words. Good morning, everyone. Thank you for joining my session today. And it's honor actually to be back here again in Taiwan. So last year, I also joined the same session. So last year, I presented a topic related with unstable formation in geothermal, which we usually call paleosol. So several people call it iron oxide, several people call it red clay. So last year I shared that kind of experience from Baker Hughes, how we manage this kind of risk. But for today, in this opportunity, I would present a different topic. So the today topic will be actually talk about how the solutions that Baker Hughes can provide in all geothermal ecosystems. And before I begin, kindly allow me to introduce myself. My name is Christovik Simatupang. I'm a geologist by background. So I have spent my career in geothermal for almost 20 years. And I'm currently working as a geothermal technical lead to navigate and oversee all the geothermal technical work around the Asia Pacific region. So before we jump into that kind of challenges and solutions, so first of all, we need to understand the geological setting. Because if we don't understand the geological setting, then we cannot actually match the solution to any challenges in each specific geothermal fields in Taiwan. So what we learn from all of the effort that's spent by many researchers in Taiwan, so there are three types of geothermal setting in Taiwan. In the northern side, it's a volcanic type, while a bit to the southern side, there is a rift type. And then in the eastern coast, there is a metamorphic rock. And we also learned from the presentation that brought by the Ministry of Economic and Affairs yesterday. So there is another type actually identified in the western side, which is the sedimentary type. And from all of the lessons that Baker Hughes has from all of the geothermal projects that we have around the globe, so for a volcanic type, qualitatively, so the temperature is relatively higher compared to the other setting. And when we talk about permeability, the volcanic one relatively also have a good permeability, and similar with the rift one. And in the metamorphic one, the temperature is relatively lower to medium compared to the other two. And then the permeability also relatively poor to fair. So with this kind of fact, then we cannot actually proceed the development of metamorphic system with a conventional system. So understanding this one in advance is very critical because it will dictate how we actually strategize our plan to develop the resource. And then when we talk about fluid risk, in a volcanic system, since there is a magma degassing process from the magma body, then the magmatic gases will be dissolved in the fluid itself, and it may actually possess these kind of like corrosive fluids. And not also to mention, because there is a water rock interaction in the reservoir, then any certain mineral may actually be oversaturated. So if we produce this oversaturated fluid and also this corrosive fluid, then this kind of condition and situation may actually can lead to these problems along the operation stage. So therefore, we need to actually identify this kind of risk in advance, even during the exploration stage, when we conduct this geology, geochemistry, geophysics survey, in order for us to be able to define what is the strategy to develop the resource. And then once we understand this characteristic, now we are going to match with the goals that set by the government of Taiwan. So we also understand and learn from the government that the government set this very optimistic target, which is good. So by 2025, it is targeted to generate around 20 megawatts. And then by 2030, government expect to generate 200 megawatt in 2024. But we also see from the presentation of the minister that it is not 200. It's actually 1.2 gigawatt by 2030. So with this aggressive target, it's very critical for us to support the government with this kind of understanding from the subsurface point of view. Because once we understand this one, now we can develop the strategy. Like, for example, this one, the one that's shown on the bottom right. So it's very, I would like to highlight and stress out this one. It's very important for a subsurface risking to be conducted as early as possible and properly. Because the geology, geochemistry, geophysics surface survey, the result will be the basis for us to actually identify the well placement, the strategy for asset development, where to put the production well, where to put the injection wells, whether it is conventional, whether it is EGS, whether it is AGS. So once we understand all of these characteristics, now we can actually capture that one into our asset development plan, right? And once we develop the strategy, we also need to also develop the mitigation plan. Why? Because we still have high uncertainty once we completed the exploration stage. We can refer to many charts that developed by many institutions like World Bank. They already indicated, based on the global geothermal projects, we learned that once we complete the 3G survey, it's actually not reducing the uncertainty to significant level. We reduce it to a certain level, but we still have the uncertainty. So we have to actually acknowledge the uncertainty that we have here in the subsurface by develop the mitigation plan. So when we drill the well, all of the target, all of the basis to do that is actually based on the surface exploration survey, right? So if the well actually encounter, let's say, low permeability or low temperature, then we have to actually prepare the mitigation plan in advance. In this case, for example, if we deal with this low temperature, then, or medium temperature, then we have a technology called ORC, or another technology that called green loop, closed loop technology, where we can still optimize the well that cannot flow with conventional way, and we can still connect the well into the power plant. And then last but not least is the fit for purpose advanced technology utilization. So why it is important? Because as a service company, Baker Hughes doesn't want to actually offer a technology that only favor us as a company. Because from our perspective, we just like offer the high cost one, and then it will favor us. But we would like to make sure our client actually get the fit for purpose one. So we would like to assess which technology that actually really needed with the given resource characteristic. Because we would like to make sure that it's not only favor the service company, our side, but also favor our client. That's how we actually can make sure that we can run a effective geothermal project. Now we move on to the simple comparison between these three ecosystems. So as we all know, these are the three resource components, the main one, to simplify everything here. So temperature, permeability, and fluid. That's how we actually understand the resource characteristic. So in the conventional system, it is very suitable if we have the resource characteristic is the temperature is good, permeability is good, fluid is there, then conventional system is the most suitable one. But if we have a challenge with any of these components, then we might want to consider to utilize either EGS or AGS. And when we talk about the megawatts deliverability per well, so in a conventional system, we can see from many projects around the globe. I will take a sample from the one in Indonesia in Sarula. So one well from the conventional system in Sarula can generate up to 60 megawatt. So, but in EGS, and we learned from the pilot test project in the US, I think, correct me if I'm wrong, the highest one right now is in range of 8 to 10 megawatt per well. So if we go to the AGS, the megawatt generation that we can expect from the well relatively lower compared to these two systems. And then when we talk about other kind of like utilization, like cascading, then mineral extraction, then we can actually expect that one from conventional system. But we might not be able to expect that kind of mineral extraction technique from EGS and AGS. Because in EGS, we cannot expect this fluid that we inject to the formation and then react so fast with the rocks and then get the chemicals from the rocks through this water interaction and then being contained in the liquid, and then we are going to extract the minerals from the fluid. No, we are going to talk about geologic time, right? So, and we talk about also deployment right now. So deployment, like most of the existing operating fields in the world right now is the conventional one. And then for the EGS, we fully aware from the previous presentation in yesterday that the deployment of EGS, we just successfully passed through this pilot test stage and ready for massive deployment. While for the AGS for this wellbore closed loop, wellbore closed loop already also passed the pilot test and ready for the massive utilization. But for the intersection closed loop, then we still need to do a further pilot test, right? So with all of this kind of given situation, then I would say the conventional will be the primary one to be developed here in Taiwan. And we can consider the EGS for the metamorphic system. In parallel, we need to develop both north and the metamorphic one. And then we consider the AGS as a mitigation plan in case that we encounter bad wells in the conventional or the EGS may not work in the metamorphic system. So that is the proposed strategy. And then when we compare the technical workflows, we talk about resource characterization, design, and simulation. So in terms of resource characterization, we need to actually understand the characteristic that I mentioned before, right? The temperature, permeability, and fluid chemistry. In order for us to be able to define what to expect and how many megawatts to be expected from the conventional system. While in the EGS, the permeability is actually not given naturally or in situ, right? So we actually enhance, we actually induce the permeability by injecting this cold fluid into the hot rocks. So that kind of technique now will actually ask us to understand the fracture characteristic. Therefore, we need to collect more data to enable us this kind of like fracture characterization study. And then once we get the data, then we can actually assess how we actually strategize the EGS deployment and also what to expect from the EGS. And then when we talk about AGS, we talk about the thermodynamic of heat extraction, because we actually just circulate this working fluid through this facility that we install into the wellbore, and then we expect this working fluid will actually sweep the heat from the rocks or from the subsurface, and then the hot fluid will actually coming up to the surface, right? And when we talk about the design is for sure different between all of the ecosystem. In the conventional, the well plasmin, the construction of the power plant, right, and all of those kind of facilities need to be acknowledging the fact that where the location of the upflow and where the location of the outflow, because we don't want to put the injection well in the wrong location, and we don't want to put the production in the wrong location as well. And we need to actually simulate through a numerical model how this certain technology, or sorry, this certain scenario actually will favor us for a long run. And then for the EGS, we need to actually do this kind of like hydraulic simulation through hydraulic fracturing and or hydrosearing to understand how the fracture will actually behave when we inject the cold fluid. And then for the AGS, we need to model how the heat extraction actually be conducted, right, when we circulate the fluid. And then when we talk about simulation, there's no much different, but the thing that I would like to highlight for the EGS case, since we might induce a microseismicity events due to this cold fluid injection, then we might also consider to simulate the microseismic location through the survey and also modeling. And for now, we move on to the conventional geothermal system. So these are the common challenges that we observe from the conventional system. So since we take out the mass from the reservoir, then pressure decline is expected, and then cooling can also be expected if we put the injection wells too close to the production wells, and scaling can also occur because of the over extraction. So we actually exceed the mineral saturation, and then corrosion may also occur if acid fluid present. And these are the potential solutions that Baker Hughes can provide to actually overcome the challenges. And we have a very strong and robust portfolio in those listed countries. So I will take an example from ORC system. So ORC can be a good solution for any low to medium temperature system. And then this is the case study that I would like to share. So I share this one internationally because I do aware that the several systems in Taiwan actually get possessed with this kind of scaling problem, and therefore it's very important to actually collect data and the good data in advance for us to be able to actually assess the risk of the fluid when we actually extract the heat out of it. And then this is the case from Indonesia, where we actually assess the scaling problem in the well, and we find out that the scaling problem actually moving to the upstream side. It was started from the separator and then moving to the two-phase line because the fluid mixing between injection and the production and produced fluid. So that's why the location of the scaling, the position actually moving to the upstream side. And we try to assess the saturation for each location as shown by the chart below. And we actually define the solution and options and coupled with the economic model. So because as I said before, we don't want just to offer the technology, but we also want to make sure when we offer the options, we also offer a option that coupled with economic model. And then for the EGS, these are the challenges: complex drilling operation, fracture opening, economic justification because of this complex operation, and also because of this lateral drilling that we perform in EGS reservoir. And then these are the potential solution, and these are the portfolio that we have in the US, also Europe and Australia. And we're glad to actually provide you support in any EGS project that you have. And this is one of the case study in Utah Forts. So we got involved in the subsurface study and also in drill bit, wireline, and also pump in supporting the success of the Utah Forts project. Sorry, because time is up, I need to speed up. So, and this is for AGS. For the AGS, as we can see over here, that we, through our strategic partner, Greenfire, they successfully do the pilot test in COSO and Geysers geothermal field, where the challenges also successfully observed when we perform the pilot test. And these are the potential solutions that we can offer to overcome the challenges. And then this is the case study from the COSO field, where the well initially doesn't produce, non-productive, but because of this technology from Greenfire, we installed the closed loop, then we enable the well to produce around 1.2 megawatt to 1.9 megawatt, depending on the type of the heat extraction technology that we install at the surface. Next. And last will be the supercritical geothermal system. I think New Zealand team is studying this one intensively, and also the Iceland. So we also got involved in this project before. So we provide several equipment and technology to support the drilling of the wells to the magma bodies. And as we know that the challenge for this one will be the high temperature, because most of the technology right now that available actually match the temperature that shown by the conventional system that developed around below 300 degrees Celsius. And then not to mention also the fluid characteristic, where in the supercritical condition, then the fluid will be very acidic, corrosive, and then there's potential for scaling as well. And then low permeability, because the location of this supercritical geothermal system will be in the transition between brittle and also ductile. So that's why low permeability may be possessed. And these are several solutions. Next. And this is the case study. For that one, we keep on improving the temperature limitation of our tool to enable the drilling of supercritical system. So as we see over here, this is in Iceland. So we enable the operation of this directional equipment for about 50 hours, get exposed to 300 degrees Celsius, and the tool work well. Thanks. And this is the last. So as presented by many Baker Hughes personnel, that we can actually promote these S2S solutions. And we believe that with this integrated solution, we can actually help Taiwan to accelerate the geothermal development, as well as we can drive the efficiency of the project execution. Thank you very much, and I welcome for any question.
Thank you. Thank you.